Okay, so where were we last time? We were trying to design an approximation algorithm for metric TSP, right? So, metric means distances satisfy going directly from U to V is cheaper than going through some other vertex. Okay, so this is the triangle inequality. We saw that without this assumption or the more general TSP has no hope of getting any polynomial factor approximation algorithm. And here for metric TSP, we want to design good approximation algorithm. We saw that the problem is NP complete because Hamiltonian cycle can be reduced to this 1-2 version. Okay, so in fact, this will use a number of algorithms we have seen in the course. So, step 1, so this is approximation algorithm. Find the minimum spanning tree in the graph. Right, my input is G, it's complete, and there are distances natural numbers. Okay. You can find minimum spanning tree almost linear time. So anyway, so what do you mean? How far? Okay. Does this condition help in finding minimum spanning tree faster? I'm not sure. I doubt. But anyway, you can find it in something like m plus n log n time. Union find data structure or Prim's algorithm, Fibonacci heaps, throw all that and you can get pretty fast. Okay. So, in your complete graph, you have found a minimum spanning tree which looks like this. Okay, so let me say this is an example. These are the vertices. First, can you relate the weight of the minimum spanning tree and the cheapest TSP tour? Because I mean, eventually we will that weight of, okay, so let me write this somewhere here, weight of minimum spanning tree and cost of optimum TSP. Weight of minimum spanning tree is greater than, less than or equal to, right? This is less than or equal to. Why is that? TSP is a cycle. So, take the TSP tour, optimum TSP tour, delete one edge, what you get is a spanning tree, right? Because it's a Hamiltonian path, so it's a spanning tree. So, weight of the minimum spanning tree will be actually less than or equal to that. In fact, if the edge weights are all non-zero, then this will be strictly less because you're actually deleting an edge from this to get a tree. So, okay. So, this will be useful. We'll come back to that, right? Delete an edge from opt TSP2 gives a spanning tree. That's the argument. Okay, so we'll come back to that. So now My goal is to get a cycle from here. Okay. So what we will do is double every edge in T. Okay, so this is minimum spanning tree to get T prime. What do I mean by this? I'm going to just do this. Okay. Now what I have is a graph which is Eulerian. Why is it Eulerian? Every degree is even because I doubled the degrees. Whatever it was, I doubled the degrees now. So T prime is Eulerian. So find an Eulerian cycle in T prime. Which we know we can find very fast, linear time. So what would be an Eulerian cycle in this would be like start from A, C, B, C, D, E, F, G, F, E, H, J, H, E, and then I come back with I, E, D, C, A. I presume. So some Eulerian to start from here, go back here. Like that. Okay, so that's what I've written down. Some Eulerian, because it's an Eulerian graph, it's find the Eulerian cycle in this graph. What will be the total cost of this Eulerian cycle? Okay, so cost of the Eulerian cycle, which I found, is exactly 2 times weight of the minimum spanning tree, which I know by here it's 2 times cost of optimum TSB. Okay, but my goal is to get a Hamiltonian cycle. But the graph is a complete graph. So I will get a Hamiltonian cycle by doing the following. I follow through A, C, B, and then say, oh, you're repeating C. No, I don't want to do that. I'll go D, E, F, G, and then I'm repeating F. No, I don't want to do that. No repetition. H is fine. J is fine, but no repetition. I, no E, no D, no C. I get A. So what is this? So I'm just going A to C to B, and then instead of going to C and then D, I will directly go to. So my Eulerian cycle will be looking. I take the Eulerian cycle, convert it into a Hamiltonian cycle like this: A, C, B. Instead of going to C and then to D, I will directly go to D, and then I will come to E, F, G. So E, F, G. From here, instead of going to F, E to H, I will directly go to H, and then to J, and then going back to E, I will directly go to I, and directly go to A. Okay. These edges are there because the graph is a complete graph. So all the edges are there. So now somehow get a Hamiltonian cycle from T prime by short circuiting. It's called this cycle as C. Okay. That's my output. Okay. So, what is the cost of the Hamiltonian cycle? Yeah, because the cost of the Hamiltonian cycle, C, the total cost, I claim is less than or equal to cost of the Eulerian cycle. Right? Because the Eulerian cycle would have taken this edge, this edge, this edge and this edge. But now from B, instead of going through these edges, I go D direct. Can it be? This is exactly the place where we use, it's a metric TSP.
So when we started with minimum spanning tree, why didn't it actually choose BD instead of BC plus C?
Oh, in the minimum spanning tree, yeah, we need to span C. So if I had chosen AC and then BD, then these edges will not be there. It will be disconnected and all that.
We could have AC and then CB edge and then BD edge. I got it.
Yeah. So I mean, good question. So question is that why did minimum spanning tree choose those edges? Well, minimum. Yeah, maybe it formed a cycle or something. That's why it didn't choose things. Right? So this is the place where we use the fact that you have metric TSP, right? So BD cost is less than or equal to BC plus CD. So that's all we are doing throughout, right? We're just going short circuiting. So apply this triangle inequality multiple times. This tour is less than or equal to cost of Eulerian cycle, which is at most 2 times cost of optimum TSP. So what we have is we have produced a cycle which is at most 2 times optimum. Okay. So again, when we argued for vertex cover, we gave multiple 2 approximation algorithms. We compared it with some lower bound for vertex cover, which was matching. Here, we are using this lower bound of weight of minimum spanning tree. Okay, so this cost of optimum TSP is at least this. So, and then we compare it with the minimum spanning tree weight. Okay, so this gives you a 2 approximation algorithm. Okay. Later, so is that clear? Is there any questions? Yeah. Yeah. The volume is not clear. Can you increase it somehow? Not so much. Okay, go try. Okay, I'll see. Multiple. Yeah. Sure. Yeah. It doesn't matter because the cost of the Eulerian cycle, since the Eulerian cycle visits every edge exactly once, it would be exactly this. That's all we are using anyway. Yeah. And then we are doing this triangle inequality. Okay. Now, this was some years ago, and then somebody came up with an improvement to this approximation. So remember, one thing is that I'm not really paying attention to the running time of these. All I am worrying about it is that it's polynomial time. Okay, you can talk about it, but the key thing in approximation algorithms is this approximation ratio. Okay, how close to the optimum you can get. Okay, that's the metric you want to get close to. I mean, you can do multiple optimization and talk about doing this fast as well. Yeah. So, and then somebody came up with an improved 1.5 approximation. It's very illustrative, so we'll go through that. So, what did we? I mean, so we doubled every edge here. What is the purpose of that? Hmm? To get an Eulerian graph. So, to make the graph Eulerian, we doubled every edge. Okay. But in T, there are already some even degree vertices. So, if you look at the induced tree, Some vertices have even degree, some vertices have odd degree. So, if somebody has even degree, why do you want to mess up with them, right? The goal is to make every degree even, just leave them alone and maybe worry only about the odd degree vertices. Okay. Okay. So, and the number of odd degree vertices will be even, okay, and it is a complete graph. So, what we will do is the following. Instead of doubling every edge, okay, this is an algorithm we have not seen, but take it from me that it is possible. Find. So, what we are going to do is to find a matching, perfect matching among the odd degree vertices. Odd degree vertices, there are even number of them. It is a complete graph, everybody is adjacent to everybody. So, you can find a perfect matching, right. There are lots of perfect matching. So, which one would you want to find? Find the minimum weight perfect matching M among odd degree vertices of T. And my T prime is T union M.
Why would there be even number of vertices in T?
Theorem 1 in graph theory. In any graph,
Okay, yeah, I got it.
right, number of odd degree vertices is even. Okay, so now, so let's see on this example what would I have done, right? Let's. This was my tree. Okay, so this is even degree already, so I won't bother. This is of even degree. This is even degree. This is even degree. So, yeah, so I only have to worry about these 3, 4, 5, 6 odd degree vertices. So, I find a minimum weight perfect matching. Now, how that's possible? Well, that's a black box, I'm not going to talk about. So, you can again do your matching algorithm and modify it to get minimum weight perfect matching. Okay. So, this minimum weight perfect matching may actually use one of these edges as well, because this is odd degree, this is odd degree. So, it might use this edge for all minimum weight perfect matching. It might use this edge and maybe this. Okay. So, now I have got an Eulerian graph, because every degree has become even. T prime is T union M. T prime is Eulerian, find an Eulerian cycle, get a Hamiltonian cycle out of it. Okay. So, now I have to argue the ratio. So, this is fine. Cost of no, this is not 2 times, it is something better. Okay. We'll see what it is. Well, cost of the Eulerian cycle is equal to cost of or weight of the minimum spanning tree plus the weight of the minimum weight matching, right. That is what it is. Okay. So, the claim is, and cost of the final, this is less than or equal to cost of the final Hamiltonian cycle. Because of the triangle inequality, I am doing short circuiting. This is less than or equal to this is this plus this. So, what I want to show, yeah, I do not think you need this picture anymore. cost of this matching, minimum weight perfect matching on the odd degree vertices is less than or equal to half cost of TSP2. Okay. To show that, what do I get? What sort of approximation ratio do I get? 1.5, 3 by 2, because this I know is less than or equal to cost of opt. This I am going to prove half cost of opt. So, overall 1.5 times cost of opt, right. So, it is a 3 by 2 approximation. Okay, so why is this? Yeah, take the TSP tour. Let C star be the opt TSP tour. Right. So, C star looks like this. This is my C star. In this, I am going to remove all the even degree vertices of T from the cycle and do a short circuiting. Okay. So, my vertices of G are partitioned into odd degree vertices of T and even degree vertices of T. T is minimum spanning tree, so every vertex is there in T. Some are odd degree, some are even degree in the induced spanning tree, right. So, look at only the odd degree vertices. So, this was even, maybe this was even, maybe this is odd, even, odd, even, let us say. So, what I am going to do is do this short circuiting, keep only the odd degree vertices and look at this cycle. Okay, just basically delete the even degree vertices and do a short circuiting, right. And look at this tour. Let us call C star O as the short circuited tour of C star restricted to O, the odd degree vertices. What can you say about cost of C? This is less than or equal to cost of C star. Same short circuiting idea argument, metric TSP, right. Now, cost C star, it contains all the odd degree vertices. It is a cycle. It is a sum of two matchings, right. Just pick the alternative edges of this O star, that would be one matching, and take the other alternative edges, that will be another matching. So, this is sum of two perfect matchings of odd degree vertices, which is equal to at most cost of this. So, at least one of them must be at most half of this. So, the minimum weight perfect matching will be at most half of it. Okay. So, let me just write what I just said. C star is equal to some M1 union M2, where M1 and M2 are perfect matchings on O. So, cost of M1 or cost of M2 is at most half cost of CO star, which is at most half cost of C star. So, you have a perfect matching which is at most half of it. So, the minimum weight perfect matching would be at most half of it, and that is what we wanted to show. This is still about 25 odd years ago. Yeah. and I think this is the best. We don't know anything better. Okay, good. So we've seen some, vertex cover, LP, and a number of algorithms we have seen being thrown at using some lower bounds, right? So this is the lower bound which we are using. Cost of opt is at least 2 times cost of a minimum weight perfect matching on the odd degree. What is this? This is another lower bound we are using. Yeah. So let's see one more example, approximation, and that is for set cover. Okay, so let me just say completed this picture is at most 3 by 2 times opt TSP cost. So this ratio now is 3 by 2. So recall the set cover problem. So you have a universe, let's say there are some n elements and then some family, okay, this is a notation which means the subset, it's a family of subsets of U, and question is find a minimum subfamily of F that covers U, right? Covers means that you take the union of the sets in F that should cover U. So we saw that this generalizes actually several covering problems, in particular vertex cover. And the best known approximation algorithm for this is the greedy approximation, which works for vertex cover also, right? So what is the greedy algorithm? Basically, I run through my F, find the set that covers largest number of uncovered elements, delete those elements from my universe and repeat, right? A black pen or red or something. Okay, so the greedy algorithm is find from F a set that covers maximum number of elements of U. Covers means contains basically. So let's say S is that set, then F prime, let's start with F prime equal to empty, F prime equal to F union the set S, and U is U minus S. Yeah, so keep repeating it until U is empty, right?
Still involves scanning over all the subfamilies like n times.
all the subfamilies. Scanning over the sets in the family. Yeah, sure. Or maybe, you can organize, you still need to scan every set in the family. Yes. Yeah. Yeah. So it will be cardinality of F times your solution size or something like that. But each set you pick, you have to run through, because even if you organize your sets in some cardinality, that doesn't help, because you have to, delete elements that have been covered. So you need to look at set that covers maximum number of uncovered elements and repeat it. Right? So for vertex cover, this is same as saying pick a vertex which has the highest degree, include it in your solution, delete all these edges, go to the remaining graph, pick a vertex with highest degree, and so on. And I said that it has that algorithm has a log n approximation ratio. So we will prove it here. Okay, it will, because that's a special case. It also follows. Okay, so let's see an example where it can be pretty bad, right? So let's see this pictorially. So I have maybe some 16 elements. Okay, so 8. I think this works for any power of 2. Okay, so this is some S1. So this is my family, right? And these are the elements. So let's say this is my S3. This is my set S4. This is my set S5. Yeah. But okay, let's even have some other S6 and S7. Okay, so there are 16 elements in the universe. And I have these sets. So the optimal would be 2 sets, S1 and S2, right? And notice that S1 covers 8 elements, S2 covers 8 elements, S3 also covers 8 elements. Okay. So greedy, if it manages to break tie by choosing S3, then not just, so it might pick S3 because it covers 8 elements. And then if you remove it, S1 covers 4 elements, S2 covers 4 elements, and S4 also covers 4 elements. So instead of picking S1 or S2, greedy may pick S4. And then it might pick S5 and S6 and S7. Okay. You can see some pattern here and extend it to any power of 2. And yes, you can also adjust it so that even without the ties, you have greedy doing so badly. So if you see the ratio here, it's like roughly 3, which is like log n by 2. Okay. So this is to point out that there are examples where not only greedy is not optimal, greedy can be pretty bad compared to opt in general. Okay, so what is the claim? So this is, but it's never worse than that. Okay. Okay, so let G be the number of sets picked by greedy, and C be the optimum. Then the claim is okay, so C, so it's never worse than log m times the opt. Okay. Okay, so this is a very intricate proof. I mean, there are several proofs. I'll try and give you what I think is sort of the simplest proof. So this is also tight. One can show by this kind of an example that there will be examples where greedy will be big, and this pretty much both the example and the analysis applies for the vertex cover greedy, and it has not been improved, this ratio log m, and it's also believed that this is the best we can do for general set cover. Okay, so how are we going to prove this? Okay, 2-3 line proof, but some long lines. Yeah, okay. So on M N actually, right, where my universe size is N. Yeah. Okay, so the proof. Let Mi be the number of uncovered elements after greedy has picked I sets. Okay, so what is M0? N, all elements, everything to be covered, right? Okay. And we will argue that actually, Mi decreases by some ratio that, which depends on C. So that's the point. You're trying to guess the proof. Next step. No. Okay. Yeah, I mean, we want to somehow argue the greedy covers every step quite a lot, so that greedy won't go for very long. That's the idea. But quite a lot compared to the optimum. Okay, so that's what we want to show. So let's see. So okay, so let's look at, so there are some so it has picked some I sets, and there are Mi elements to be covered totally, right? Now, but there is a way to cover these elements using at most C sets. Agreed? because the optimum covers the whole thing. So, that means that one of the sets remaining has size at least mi by c, right. So, at least there exists a set with greater than or equal to mi by c uncovered elements, because C sets are enough to cover this, right. And greedy picks the largest uncovered elements. So, greedy will cover at least this many elements. Okay. So, what can you say about mi plus 1? After greedy picks this would be less than or equal to mi minus mi by c, right, because yeah, mi elements are to be covered after I steps have been. So, let's say I picked some greedy, I picked some 1, 2, 3 up to some I set, some sets. Okay, S1, S2, Sn. So, mi elements are to be covered, but they are spread over various sets. But there exists a set with at least mi by c uncovered elements, because sets are enough to cover the entire thing. So, even this. So, greedy will pick that set or even something with a larger set of elements. So, what is left would be this. Okay, that is all I need. Now, I am done. Okay. So, what do I want to show now? So, and if I telescope this, what do I get? I get that mi is less than or equal to 1 minus 1 by c whole power I times n, right, because m0 is n. So, m1 by this would be 1 minus 1 by c times n, m2 would be 1 minus 1 by c whole square. So, mi is this. Okay. Okay, so just to make life simpler, let us say greedy picks some g plus 1 sets, okay, instead of g sets. Yeah, so this is what I want to show. Right. So, number of sets picked is just g plus 1. Okay. So, mg is at most 1 minus 1 by c whole power g times n. After greedy has picked g sets, the number of elements to be uncovered is at most this much, and it must be at least 1, right. Why at least 1? Yes, because of that. Because greedy needs one more step to complete it. So, mg is at least 1 and at most this. Okay. Now, that is it. From here, I want to bound g, right. So, what do I get? 1 is less than or equal to 1 minus 1 by c whole power g times n. Right. Separately, we will show, or it is easy to see, that 1 by 1 minus c is less than or equal to e power minus 1. Yeah, because why? Because e power x is greater than or equal to 1 plus x, right, for any x, for the 0, negative, positive, because by Taylor series e power x is 1 plus x square by 2 factorial and so on. So, now instead of x, if I put e power minus c. So, now if I put x to be, what do I have to put? 1 by c, then I have 1 minus 1 by c is less than or equal to e power minus 1 by c. Okay. So, minus 1 by c, sorry. So, I am going to write this as e power minus g by c times n is greater than or equal to 1. Okay. Yeah, we are done, right. So, e power g by c is less than or equal to n. So, g by c is less than or equal to ln n, g is less than or equal to c times ln n. Okay, so that is what I wanted to show. Okay. I mean, I don't know what the intuition is, but it just, there are multiple proofs for this. This is the slick proof I think I found. This is a tight bound because of this example we have.
But then G here is equal to 5, C is 2, and N is 16. So that gives us 5.
Okay, so maybe there is a constant. Sorry, what did you say? G is?
G is 5.
Okay, there is a natural log. Okay, this is not log. You may still be right. It may not be tight. First of all, this is not log base 2 as we always use, because this is log base E. Yeah, I mean, yeah, it still may not give you the exact tight bond, but it's just this omega log n and big O log n is the ratio. Okay. Good. So what else we can do? So we can do now. Okay. So that's all. A bit an approximation I want to give you. We've seen vertex cover, set cover, TSP, and there are more in the books. And one can do a whole course on approximation. Lots of nice machineries have been developed. Okay, I can quickly do some approximation for SAT and cut. Okay, using some idea of randomization. 5 minutes on that. Okay. Now, look at the satisfiability problem, right? Given a formula, is it satisfiable? Approximation makes sense only for optimization problems, right? Satisfiability is a yes or no question. What is there to approximate 0 or 1? Okay. But what we can do is there is this max SAT problem. This is another well studied problem where, given a formula, CNF formula, you want to find an assignment that satisfies the maximum number of clauses. Okay. Or given an integer k, can you satisfy at least k clauses? This is NP complete even for 2 SAT. Even though for 2 SAT, can you satisfy them all is a polynomial time problem. But if the answer is no, you ask, okay, can you satisfy at least k clauses? We don't know that. That's an NP complete problem. Okay. So, at least for 3 SAT and above, you see that this is a generalization of SAT, right? Because SAT says, can you satisfy them all? This says, can you satisfy at least k? This is NP complete. So, now we want to approximate this number. How many clauses can you satisfy? Okay. So, there is a very simple approximation through randomization. Okay. So here is a formula which looks like this. And what we want is, is there an assignment that satisfies, or give me the assignment that satisfies maximum number of clauses. Also, in contrast to whatever we saw, this is a maximization problem, because we've seen vertex cover, TSP, set cover are all minimization problems. This is a maximization problem. So you have to look at the ratio slightly differently. Okay, but so you want to satisfy at least a good fraction of the clauses, good fraction of the possible number of satisfiable clauses. That would be a good approximation algorithm. Okay, so what happens if I just do a random assignment? What does a random assignment means? For every variable, I toss a coin. If it comes head, I set it to true. Otherwise, I set it to false. And look at that assignment. Now, since it's a randomized algorithm, I can only talk about the expected number of clauses satisfied. So, what would be the expected number of clauses satisfied? Well, this is run over all the clauses in the formula. Probability that C will be satisfied. Right? Yeah, what is the probability that a clause will be satisfied? In a 3 SAT, right? If you take a 3 CNF, every clause has 3 variables, then what is the probability that any clause will be satisfied? Well, there are 3 variables there, 8 possible assignments, all except one will satisfy them, because there is only one way in which you can falsify them. So this, with probability 7 by 8, it will satisfy that clause. So this linearity of expectation says that you can actually satisfy 7/8 over half the number of clauses. So this is a sort of a ratio 7 by 8 opt, because opt can at most be C, total all the clauses. Okay. But if it's a general SAT, I don't tell you 3 CNF. Okay, a clause can have even one variable. Then what would be the probability? Well, whatever the length is, 1 minus 1 by 2 power the length. If the length is 1, it's only half. Okay, so you can only say you can satisfy at least m over 2, half the number of clauses. Okay, so that's a ratio half approximation. This can be de-randomized, improved using linear programming and all that. Okay, so this is another nice, well-studied problem, MaxSat. Okay, some heavy machineries of linear programming. Even one more level, semi-definite programming has been used to improve the approximation ratios here. Another very similar problem is max cut. In fact, you can de-randomize this. Okay, by de-randomize, I mean that you can actually deterministically find an assignment that satisfies at least 7 by 8 of the total number of clauses. Worst case, because I can de-ran, I can find deterministically an assignment. That requires something I can tell you later, maybe, if there is interest. Okay. But the point I want to mention is the power of randomization. Okay, it's very simple random assignment. Bang, you can get this. A related problem where such randomization works is the max cut problem. Okay, so the problem is you're given a graph, partition V into U and W such that max number of edges go across U and W. Right? So maybe your graph is. Then I want to partition so that maybe I'll partition this in one side and this in the other side, so that 3 edges are going across. I want to maximize the number of edges, so it's max cut problem. Okay. If I want to minimize the number of edges going across, can we solve it? No, we have seen it in our class. Yeah, but max, okay, you can apply max flow min cut theorem to get min cut, right? But max flow min cut theorem requires you to have two vertices. It's only max ST flow is equal to min ST cut. Okay, but try all STs. So in polynomial time, you can find if I ask you min cut, okay, but the max cut is NP complete. Okay. Now I want to get an approximation algorithm. Can we do something like this? What is my goal? What do I want to do? I want to partition the vertices. For every vertex, toss a coin. If it comes 1, put it in the set. 0, it goes in the other set, right? Head or tail. So I get this set. Random partition. What is the expected number of edges in the cut? Well, let's argue exactly like this. Sum over all edges. Pick an edge. What is the probability that it is in the cut? Yes, what is that probability? 1 by 4 this way, 1 by 4 this way. Right? So, what is the probability that when you toss coins on the endpoints of these vertices, you get different values, right? 1 0 or 0 1, both of them. So, 1 by 4, half into half plus half into half. So, half. So, expected number of edges is very similar like here. Is m over 2. Okay. This is like a half approximation algorithm again, because the maximum could be m and I can get close to half m. You can de-randomize this, you can improve this using semi-definite programming and all that. Okay, so no, undirected. Okay, so much on approximation. Let's move on. I want to talk about. So we have seen approximation. We have seen little bit on exact algorithms, right? Graph coloring and set cover. I was talking to you about, and special instances is another thing, right? So let's look at a quick intro to parameterized complexity. Okay, so what's the idea here? Basically now, so far our, we had input and there was some input and our algorithms were, we were analyzing it on a function of the input size. So whether it's polynomial, exponential or whatever, right? So in parameterized complexity, what is the idea? We want, so your input comes with some parameter k, and I want to analyze the algorithm's performance with respect to the input size and the parameter. Okay. Now the parameter could be anything which makes sense. So in practice, whatever parameter. So if you are looking at graph, maybe the parameter can be the maximum degree of the graph. It could be solution size. If you are looking at some string problem, the parameter could be the alphabet size, or anything, right? And in particular, we want algorithms which is on the parameter. It could be anything, it could be pretty bad, it could be exponential, double exponential, but it's polynomial time otherwise on the input size. Okay, so the idea is that if the parameter is small, you still have a decent algorithm. Okay, so yeah, so maybe for the sake of some of you who know all this, let me give you an interesting problem, even new for you. So let's look at the vertex cover problem. What can you do on a tree? Suppose I tell you your input graph is a tree. Okay, can you solve it in polynomial time? We saw it last time. This is a hint. We saw it last time. What? Matching. Tree is a bipartite graph, right? Is a tree bipartite graph? Yes, because it has no odd cycles. Because it has no cycles. And we saw that in bipartite graphs, Koenig's theorem can be used. So maximum matching is equal to min vertex cover. So you can solve min vertex cover in tree using the bipartite graph black box. But we can do something even simpler. Okay. So what did you say? Maximum degree. No. What do you do? Leaves. Okay. So let's just. Okay. So here is. Suppose you have. This is my graph. Okay. So it may or may not be a tree, but if I have a vertex with degree 1, can you pre-process it somehow for vertex cover? What can you do? Yeah, so I want to find the minimum vertex cover in the graph. So it may or may not be a tree for now. Okay, so I'm just saying in general, if I have a vertex with degree 1 in the graph, here is a simple pre-processing you can do to when you are trying to find the minimum vertex cover. You can just say, hey, this edge has to be covered. So x or y has to be picked in the solution. Why do I want to pick x? So just pick y into the solution and delete the whole thing and move on to the remaining graph. Because y has done its job. And how do you argue the correctness? Because if instead of y, x was there in the optimum vertex cover, just delete x and put y and you've done the job. So without loss of generality, pick y into the solution and delete. Or it may remain the same for all you know, because you might, maybe the optimum has x but does not have y and it has something else, but then you remove x and put y. Optimum also has y, then you can just delete x, right? That's sort of the short proof of correctness. So this is something you can do in a general graph, not necessarily in a tree. If you have a general graph, here is a simple degree 1 rule to do pre-processing. Since it's a tree, if you are given a tree, you can always find the leaf. And what happens if you keep doing this? It will be done, right? Because it's a tree, you will have a leaf, pick its neighbor. Now the neighbor has done its job, delete it. In the remaining graph, it's a tree, you will have a leaf, find its neighbor, keep doing it. You can find the minimum vertex cover. This is minimum vertex cover, right? Okay, so good. So minimum vertex cover. In fact, with careful thing, you can actually implement the whole thing in poly time, on linear time. Okay, but let's not bother about it in polynomial time. So now I tell you, suppose okay, the graph is not a tree, but it is tree plus some k vertices. Okay, so this now I bring in this parameter k, right? So I want to say that the graph is somewhat k distance away from a tree. And by k distance away, I mean that there are some k vertices whose deletion makes it a tree. I will give you those k vertices as well. Okay, finding them is another problem, but suppose I give you those k vertices. Now, so input is g k away from a tree. What does that mean? There exists some S is contained in V, cardinality of S is at most k, such that G minus S is a tree. And I give you that set. So this is a tree, the remaining is the tree. Now the question is, can I find the minimum vertex cover in this graph? First question, can I actually find it in polynomial time? Polynomial in n and k?
This keyword is just like even take this keyword into the solution and then
Why should I take those k vertices? It may or may not be the optimum. Okay, why? How? Okay, so first question is, can does this exist? Does there exist an algorithm that runs in poly in n comma k? Yeah. I mean, your intuition that you can solve, I mean, any graph is a tree plus k vertices, no? Okay, I can give that. I mean, you give me a graph, I'll give you that k vertices. Any graph I claim is a tree plus k vertices for some k, right? No? Any simple graph, I keep an edge, delete everything else. That edge is a tree. So that k is n minus 2 vertices, right? So any graph is actually a tree plus some n minus 2 vertices. So if you have a poly in nk algorithm, then that would be a poly algorithm for minimum vertex curve. Okay? So this is no hope. Okay, so something you have to be exponential in. So what I'm now saying is, it's not, can you be exponential in this k and polynomial in the rest of the thing, because k is small, it's not very far from a tree. So there must be some gradation in the running time, right? For trees it's poly time, but as k increases, maybe time increases, but if k is small, I have a reasonable algorithm. So that's what parameterized complexities are about, right? So you want an algorithm which is some f of k times into the c, where k is the parameter. In this case, I decide to choose the parameter as the distance from a tree. Parameter can be solution size, parameter can be anything, and you have whole range of combinatorial questions to explore in this world. But anyone wants to take a guess for an algorithm of this type for this problem, for minimum vertex cover?
some over k choose
Hmm?
some over k choose
Some more. Hmm.
some subset of vertices into the solution and
Okay.
still
Is that a guess or is that a whole algorithm? Do you see the whole algorithm? Okay, so we want to find the optimum vertex cover in this graph, right? So here is my algorithm. Guess the intersection of, okay, S intersection opt. Okay, opt is my the set I'm looking for. I'm going to try and guess S intersection opt. What does that mean? Try all possibilities of subsets of S as the intersection, right? Guess mean try all subsets of S. So what does that mean? That I have decided to choose this subset into the solution, which also means that this is not in the solution, because I've decided my guess of opt intersection this. Okay, so let's call this yes and no. Okay, now what can you say about
If there is an edge in that end part, then we have to
go to the new guess, right? If the induced subgraph on n has an edge, who is going to cover that edge? Right? Only one of those endpoints, but you've decided not to take any of them, so this guess is wrong. Move on to the next guess. Right? Guess means try all possibilities. Right? Abandon and move to the next guess. Okay. So now this is independent, right? Because if there is an edge, we would have moved. This is independent. Now look at edges incident on these vertices. Who's going to cover them? They are the other endpoints, right? You're forced to pick them if you made this guess, right? Pick the other endpoints or pick the neighbors of n. Intersection v minus s, right? All the neighbors which are here, pick them, their neighbors, because those edges can only be covered by somebody here because you decided not to include them. That's it. Now, whatever you picked, you can delete s, you can delete whatever you picked. What is left is a tree or a forest rather, right? What is left is a, delete them. What is left is a forest. Find opt. So find the minimum vertex of the remaining graph. So include them and your guess. That's the set of vertices you decided to pick for vertex cover. Try all possible guesses, even starting from empty set, and pick the one which is the minimum. That's a optimum vertex cover. You can prove because you're, it's essentially try all possible things. How much time have you spent? You're guessing all subsets of S because S is of size k, it's 2 to the k, and whatever happening inside is polynomial time because you're checking for edges, you pick the neighbors, and what is left is a forest. So the whole thing would be some 2 power k times n power c. Okay, so in a sense, I would put parameterized complexity as, extending this special instances thing, right? We say, oh, if the graph is an interval graph, you can do very well. So now maybe I will extend it a little bit by some parameter, and can you, smoothen. Ideal would be, oh, it's bipartite graph. You have this algorithm, and the other extreme is some special, and you can. This is 2 power k tells you, right? Because this doesn't give me a polynomial time algorithm for general vertex cover because k could be as bad as n minus 2, but for k is small, you have a reasonable algorithm. Okay, so now the other question you can ask is, can you find S? How much time does it take to find S? Okay, let's ask a different problem now. Okay, so maybe I would even not say tree but forest. This whole thing works even for this, right? So, your input is G and I give you a parameter K. Question? Yeah? Yes. Yeah. And the question is, does there exist an S contained in B such that G minus S is a forest? This is exactly the feedback vertex set problem. Which is NP complete. What would be a brute force algorithm for this? So, you can try all k size subsets, delete them and see whether the remaining graph is a forest, right. Checking whether a graph is a forest is easy. So, so in the optimization version, a brute force algorithm would be like an exponential algorithm, whereas here it is like try all k sized subsets. So, that is like an n power k some polynomial time algorithm. But this is not a good algorithm in this framework because, so this is not of type f of k times n to the O. But there is one such algorithm, okay, somewhat involved. But the point is that, that is what parameterized complexity is about. Often it is n power k versus some f of k n to the c, right. What sort of problems have this kind of an algorithm is what it is about. And what makes it interesting is, just like this NP hardness theory, there is also a notion of hardness in this framework. In fact, even approximation also has certain hardness. One can prove that, for example, set cover cannot be approximated better than log n ratio unless something happens, some complexity collapse happens. So, similarly here there is a notion of hardness theory. Okay, I think I will stop here. Hopefully these two lectures gave you a flavor of different directions to deal with this notion of NP completeness, and as I said, each one is a full course by itself.